Okay, cool. Yeah, so welcome to my presentation. It's on local writing in dependent type theory, and so I'm just going to start with some motivation and explain what that title actually means. So I guess, yeah, as a starting point, why do we care about dependent type theory? Well, partially it's a foundation of proof assistance, which we can verify software in, or verify even like hardware specifications and memory models. So that's, I guess, at least the computer science perspective and why this is useful. And then also dependent types are increasingly becoming popular in programming languages to maintain invariance while writing your programs. So you have fully dependent type languages like Idris, then also languages like Haskell, OCaml, Scala, even like TypeScript to an extent are like taking at least ideas from dependent types. So progress on making dependent type theory better means hopefully we get new features in all of these different languages. And so to get a bit more concrete about what dependent types let us do, here's like a very simple example where we have this thing called a pi type, where it's essentially a function where the result of the function can depend on the inputs. So this is a function from two natural numbers, and then the result is an identity type, which is a type that's only inhabited if the equality here holds. So if you provide a program that satisfies this type signature, you've proved that addition is commutative. However, a drawback of a lot of tools based on dependent type theory is that they have quite limited automation capabilities, and especially with respect to something called equational reasoning, which I'm just going to show more concretely what this means by an example. There we go. Okay, so this is the Agda proof system, and here I'm going to be proving that for any function from Boolean to Boolean, that f of true is equal to f of f of f of true. And so I've called this theorem or whatever f3 here. And we have a hole, which is like an unfinished program, where to fill the hole we need to prove that f of true is equal to f of f of f of true, right? And yeah, the syntax here is obviously a little unusual, but the main point is that the way we can prove this is by case splitting. So we're going to first look at what the result of f of true is. This is either going to be true or false, and then we can make a bit of progress. So we can first split on the result of f of true. And again, the syntax here is maybe a little unusual, but the point is that we're going to have two new branches. And the goal type in each of these kind of cases is unchanged, so we still need to prove our original goal. But now we have the premise in the left branch that f of true is equal to true, and in the right branch we have the premise that f of true is equal to false. And actually, in the left branch here, hopefully it's somewhat intuitive how we can prove the goal here. We can just simplify the f of true multiple times to get the same thing on both sides. But in Agda, we have to do this very manually. So for example, we can apply f to both sides of the equation, and we get f of true is equal to f of true. And then we can apply f to both sides again. And then we can compose with what we just had. And now we proved the goal, but it's the wrong way around, and so we need to also manually apply symmetry of equality. And now finally we've finished that case, and now we need to deal with the false case. And actually, to make progress here, well, we can simplify this f of true to false, but then we need to know what the result of f of false is, so we actually need to do another case split and even more equational reasoning. So I won't go through that now, but I completed that earlier. And so the result is like quite a convoluted proof for, I guess, for a relatively simple property that you might expect the computer to be able to automate.
Okay,
Sorry.
Step back.
Yeah, sure.
So every function from Boolean to Boolean satisfies the property that
Yes.
f of true is...
Yeah, so if you consider cases, so for example, the identity function, this is obviously true because both sides become true. For negation, you have negating true once gives you false, and negating true 3 times gives you false. And then you have the function which always returns true or always returns false. And again, so if f always returns true in both cases, then both sides are true.
So it's very remarkable that the proof doesn't have to go through all those cases.
Well, I guess the two cases that are important here are the result of f of true, whether that's true or false, and the result of f of false, whether that's true or false. And yeah, so I guess what's kind of interesting is we don't have 4 cases here. There are 4 functions from Boolean to Boolean. We only actually need 3 cases, and that's because if we know that the function returns true in the true case, like that's enough, right? Because we're not referring to f of false anywhere here. So I guess that's the intuition. Cool. So yeah, that equational reasoning can get a bit tedious, but actually even more significantly, for like larger developments using dependent types, we like to use this thing called index types. So the idea here is we want to maintain an invariant intrinsically in our program. For example, rather than working with lists of any length, we might want to work specifically with vectors of a known natural number length. So that, for example, if we concatenate two vectors, the result of concatenating a vector of length n and a vector of length m should be a vector of length n plus m, right? And this means, for example, we can safely look up into vectors if we know that the index we're looking up is less than the length of it. And then another example of like an index data type, which is quite nice, is if we're like formalizing a type theory or implementing a type checker, we might want to work with terms indexed by a context. So that's a list of variables and their types that are in scope, and also the type of those terms. So essentially, the extra trouble you get when working with these index data types is to implement operations on them. You need to mutually implement the actual operation, the algorithmic content, but also do equational reasoning. To prove that the indices line up. And then the real problem comes from, because you can't ignore this equational reasoning, it's called transport, and it's like part of the term itself, for reasons I don't really have time to get into. But essentially, when we then prove equations about operations on index data types, you have to account for transports moving around. And so there's this really horrible lemma, for example, in the Agda standard library called transp-application, which essentially lets us push around these transports under these function applications. And I mean, it's quite a horrific looking type signature, and it's really painful in practice to apply this lots of times. And you'll see a lot of papers, even recent papers, doing formalizations, talking about this problem of transport hell, and how they try to find workarounds to avoid it. So, the main contribution, or at least one of the contributions of this project, is a type checker that can at least automate the example we saw earlier. So the syntax here is a little bit different. Id is standing for the identity type. So again, we're proving the same theorem that f of true is equal to f of true. Id is standing for like equality between this left-hand side and this right-hand side, right? And so we still need to do a case split in this type checker. And we do a case split with something called smartif. And I'll get into the etymology of that in a little bit. But the important part is that in each of the branches, rather than doing manual equation reasoning, we'll just write refl. And refl stands for reflexivity. Essentially, we're asking the type checker to do the work of actually proving the theorem with the premises in each of these cases. And so sure enough, that type checks. And then just to prove this is actually a type checker, I'm not printing success always. If I slightly change the theorem to, if I slightly change it to only apply f twice, so this isn't true, right? If f is not, this is going to fail because not of true is false, but not of true is still true. And if we try to prove that the exact same way, we will get a type error. Yeah, and I mean, this is a prototype type checker. The type errors are maybe not the most readable, but the point is we get an error. So yeah, concretely the contributions are that we present some formal work describing this like new type theory, where we can automate these equality, and we call this built-in equality that the type checker can automate. We call this conversion, or sometimes definitional equality, as opposed to propositional equality, which is the variant where we have to reason with manually. And so to decide this conversion relation, we rely on some actually quite simple techniques from term rewriting. So the real complexity here is integrating these with dependent types so we maintain decidable type checking, so we can actually have a computer implementation. And then the concrete contributions is we have some formal results and proofs that I'll explain in a bit, and then also obviously that type check implementation you just saw. Okay, so the key idea here is to, rather than just defining terms in our language with respect to a set of variables and their types, that's the usual definition of the context, we're also going to embed in the context convertibility assumptions, definitional equations, that the type checker needs to make use of. So, for example, we can express this principle with this typing rule, where we say, if we have a propositional equality, so that's key here, that t1 is equal to t2, then we can embed that into the context and continue writing our program inside of u here. And maybe a more standard-looking typing rule would look a bit more like this, for example. So using turnstile and colon to denote the types of terms, but this is kind of an intrinsically typed variant. But the point here is that we need to, is that this typing rule actually leads to undecidable type checking, and you can look in the report for the example of how. So we need to somehow restrict the type of equations that we're considering, that we're going to embed into our context. And so a nice starting point that at least lets us deal with that example we started with is focusing on equations where the right-hand side is a closed Boolean. So that's like the Boolean literal true or the Boolean literal false. And that's enough to type this rule that lets us do case analysis but then make automatic use of the fact that the scrutiny, right, the thing we're matching on, is equal to true or false in each of the branches. So that's kind of our starting point. And then to make this a bit more formal, kind of the new part here, so we define a substitution calculus. Substitutions are how we map terms between different contexts, and so it's required to define the type theory, you need some sort of substitution calculus. And then kind of the new thing here is because we're extending the context with these convertibility assumptions, we need to describe what it means to substitute from a context with an assumption to one that might not have it. And essentially what it means is that after substituting both sides, they also have to be definitionally equal in the context we're mapping into. So anyway, so we can describe the substitution calculus, kind of this type theory, right? And in my project I've done this. It's mechanized in Agda, and you can prove soundness by interpreting back into an ordinary intentional type theory. So the idea is that of the soundness proof here, we're specifically referring to consistency relative to, say, Agda or MLTT. We turn all of these convertibility assumptions back into propositional qualities. So that's why it's kind of conservative. However, so we have soundness, which is nice, but for an implementation of a type theory, we also want to have decidable type checking. So we need to have a way of actually deciding this equivalence relation here, the definitional quality, right? So to decide an equivalence relation like this, we use the technique of normalization, where the key idea is we take families of equivalent terms, we map them to a canonical representative term. So that process is called normalization, the resulting representative is called the normal form, and we decide the original convertibility relation by just syntactically comparing our normal forms. And then a specific technique to get these normal forms is called normalization by evaluation. And the idea here, very vaguely, because I don't have time to get into the details, is we construct a model. So families of equivalent terms are mapped to the same values in this model, so we call this evaluation. And then as long as we can also invert the model construction, we can get back to syntactic terms that we can actually compare our normal forms, essentially. So that's a standard technique for proving decidability of conversion in dependent type theory. And this even works, maybe slightly surprisingly, in inconsistent contexts. So I'm going to call an inconsistent context one where we have a propositional equation, sorry, specifically propositionally inconsistent context. If we have a propositional equation between, say, true and false, which is obviously a false equation, but we still want to be able to normalize terms under it, actually normalization still holds, because although from this equation we can prove that all types are propositionally equal, the manual transporting, which I talked about a bit earlier, essentially the manual equation reasoning, gets in the way when you try to evaluate terms that abuse this. So normalization still holds. Unfortunately, when we make these equations definitional, this no longer works. When all types are definitionally equal, we might as well be working in untyped lambda calculus, and obviously in untyped lambda calculus it's standard that we can write looping terms. So then the specific thing that fails in MBE here is that evaluation might end up looping if we apply it in a definitionally inconsistent context. So we need to somehow avoid ever evaluating under such contexts. Problem is deciding consistency is not necessarily easy. You might need to compute a bit on the left-hand side of your equations to actually reveal that there is an inconsistency. Now there is a technique from term rewriting which can potentially help us here, and the idea is completion. Very intuitively, we take our set of equations, we orient them. In our case, orienting is easy. We just make sure the boolean is on the right-hand side, and then repeatedly go through our set of equations and simplify them. So for example, if we have a redundant equation like true equals true, we can just throw it away. If we have an equation where the left-hand side is reducible, then we reduce it, and we've made some progress that way. And if we end up with an equation like true equals false, well then we know our context is inconsistent, and we can conclude that. And then if this succeeds, if we don't find inconsistent equations, we end up with a confluent term rewriting system, which essentially doesn't run into the issue here. So that's nice, but to actually justify completion, you need some well-founded order. You need to justify that actually doing this simplification keeps making progress. And in the report, I describe how you can do this for simply type lambda calculus, but extending that ordering to dependent types seems really difficult. And actually, so an alternative approach we could do to try and fix this is we could try to avoid completion by just forcing the programmer to only introduce equations that we know won't create inconsistencies. So like a nice invariant we might try to make sure is that all the left-hand sides are stuck, so we can't compute with them any further. and also that they're disjoint. So for example, this context here, gamma, we have two equations, but because the left-hand sides are disjoint, they're two different Boolean variables, we know that we can't get any definitional inconsistency here at least. However, the problem with trying to enforce this restriction is that it's unstable under substitution, and this means essentially you end up breaking subject reduction if you commit to something like this. Essentially, if I substitute y for x here, then I have an equation x equals true and an equation x equals false, right? And we're back to an inconsistency. So we need stability under substitution. And actually, stability under substitution has more problems. It rules out some potentially more interesting equations. And there are actually even more difficulties with normalization. You can look at the report for the details. So, kind of the final contribution to this project then is to describe a second type theory that will try to get rid of this issue. And the key idea here is that instead of having fully local case splitting, which can happen underneath lambda abstractions, and therefore we need to worry about variables being substituted, we're going to move all the case splitting to the top level, to essentially top level definitions. And then because definitions have a property where we only expand to the body after the pattern is satisfied on the nose, then we can essentially guarantee that we'll never be substituting variables underneath equations. So this idea actually very much inspired by Agda, which does a similar sort of thing, but for slightly different reasons. So Agda lets you do intermediary pattern matches, like here we're comparing two natural numbers and returning whether one is greater, one is, it should be GT, I guess, greater than, less than, equal, whatever. And then the idea here is that each of these, with abstractions, are turned into a top-level pattern matching definition. So the first with abstraction is turned into complex 1, and then the second one is turned into complex 2. So we essentially perform the same translation. So on that earlier example we started with, we turn the outer smart if into f3 aux 1, and the inner one into f3 aux 2. And the key new thing that makes this work is that definitions can ask for earlier equations. So the point here is that we can nest case splitting, and we want the previous equations that we've learnt about to still hold even in the new case split. So therefore, to make this work, we're allowing f3 to ask for a definitional equation between f of true and false. We essentially allow that, and then we also say that in the branches of our definitions, we can introduce these new equations, and then after doing that, we're in a much better behaved theory. There's one subtle issue that you might want to discuss here, which is that from the perspective of the surface language, if I write two different programs that do pattern matching, they're going to get elaborated to different top-level definitions, and if these calls to these definitions are stuck, even if the bodies are themselves equal, because the calls are to different definitions, and we're considering those to be like generative, that they're called to like distinct definition variables, right? Then from the perspective of the surface language, you kind of lose the congruence property. But the important thing here is that at least the core theory is very well justified, it has congruence, and actually the translation from the user perspective to avoid these issues is just to repeat whatever case split the definitions are doing, and then the equation will be satisfied. So anyway, in SC-def, which is what I'm calling this like new theory where we have these top-level definitions, normalizations by evaluation mostly just goes through. We have to make a few adaptations. So we need to start with some complete term rewriting system, and then unquoting, which is this process where we have a stuck term and we need to embed it into the model. Unquoting first needs to check whether this stuck term, beta stuck term specifically, is somewhere in our term rewriting system. So we can replace it with a Boolean. And then we still need to obtain this term rewriting system, but because we don't need to worry about stability under substitution anymore, we can apply any restriction we like. And so, for example, quite a good one is, like we discussed earlier, we want all the left-hand sides to be disjoint. And this still requires the user to, for example, be careful in how they order their case splits. You need to not case split on something that's a subterm of a previous thing you've case split on. I don't know. It is what it is. So anyway, conclusions. Introduce these two type theories, right? SC-ball and SC-def. Prove soundness of both by constructing models in Agda. And then also normalization by evaluation is mostly mechanized in Agda for SC-def as well. And then also the type checker, which you saw earlier. And then future work, obviously it'd be really nice to look at equations where the right-hand side isn't necessarily a closed Boolean, right? So work on more interesting equations. We could maybe look at looking at left-hand sides of equations that aren't necessarily disjoint. So I think you need to go back to completion here, and you need to find the well-founded order, but perhaps that would be a lot easier now in SC-def. Now we don't have these stability under substitution requirement. Yeah, perhaps it would also be nice to look at equation schemes. So far these equations are just between concrete terms defined in our current context. But some equations, like for example, x plus 0 equals x, right? This should hold, in theory, for any natural number type term. And so, using this kind of approach, we still have to manually invoke the lemma we want and say what x should be, where we need to use it. We just don't need to manually say how to apply this equation, just which equations we need. But maybe extending to equation schemes could resolve that issue as well. And then obviously it'd be really nice to have an implementation in a modern proof system. I don't know, I'm partial to Agda, but that obviously requires analysing the interactions here with lots of other of Agda's features. Cool, thank you.
Yeah, I'm out of my depth. Okay, so I introduced David Davis. He's my PhD student. He works on the theorem proofers and he's done co-supervision. Perhaps not as many hours as me. So I will give the floor to David.
Yeah, compared to before, the way you elaborate is similar to Agda with abstractions. How is what you've done different to with abstractions? What do you get?
Yeah, so, yeah, there's kind of, I guess, two things that I mentioned. Yeah, here, right. So, part of it is being able to reuse earlier equations. So, that's that definitional equation which I talked about that you can put in the telescope, the set of arguments of this definition, right? So in Agda, you can only ask for a propositional equation between f of true and f of false, and so you'd have to still do manual equational reasoning in here. But actually, it's even worse than Agda as well, because Agda technically does allow a subset of something that looks a bit like equality reflection, in terms of if your left-hand side or right-hand side of your equation that you're matching on, your propositional equality, because you can pattern match on propositional equalities in Agda, but if your left-hand side or right-hand side, this only works if your left-hand side or right-hand side is a single variable, because Agda can then deal with this by substituting that single variable for whatever the other side is everywhere in the term. Also subject to an occurs check. You can't have the variable occur in both sides. So that deals with some equations, but for example, it doesn't deal with ones here, right? So f of true equals true. Neither side of this is a single variable. So we can't resolve this with substitution. We need an actual rewrite here to make it work.
Okay, I've got a question. So, here's an idea. Okay, so you came into my office saying I want to do X. Okay, and now at the end you stand here and you have done Y. Compare X and Y.
Sure, yeah. So I think the original goal was still relatively similar to this. So I was talking about reflecting propositional equations. I maybe was hoping to not only focus on Boolean equations, would probably be the biggest limitation. So yeah, I was looking at, actually I didn't really mention, the original idea of adding equations via case splitting is not new. So this is something called, where was it? Yeah, here, Smart Case by Altenhurst et al. And I mean, I came to you, I think I wanted to implement a type checker, which I guess I did, for this sort of smart case thing. I wanted to do some meta theory, which I think I did. I proved soundness and normalization. Maybe I wanted to do more meta theory, but yeah, the time, what at the time, I guess, yeah, trying to get it done in time was a struggle. And then I guess maybe the other thing to mention is I talked about, I guess a few other things I could have done, right? So I think originally when I was thinking about this project, I wanted to actually implement it in Agda, and there wasn't really time to do this. Looking at more interactions with stuff like univalence, like other type system features. So I think it's a subset of what I originally proposed to you, rather than a different topic.
Yeah, but I think that also just limited to Booleans, I mean, it sounds like a banal thing, but it made a cascade of all these problems that popped up, like the comparing left-hand side and turn right.
Yeah, well, I think I would have hit these similar issues even if the right-hand sides weren't just Booleans, right? So one quite nice behaved set of equations is where both sides is a stuck term, because now if you exchange either side of that equation, you're not going to unblock any more computation elsewhere because both sides are stuck, right? So that's maybe a nice class of equations, but it would hit the same stability under substitution problems, because like a Boolean variable b is a stuck term, but if we substitute b for true, well, a true definitely isn't a stuck term because it can unblock if then else expressions. So I think I would have hit similar issues. Yeah.
Just to be concrete on the thing that like the main contribution is that in Agda, we had all that equation reasoning, we had to write con, we had to write no, and then in your language, all you have to do is write reflexive.
Yeah.
Yes.
Yeah, that's the main contribution, I guess, until you start looking at index types. But that's kind of a slightly further off motivation, right? But yeah.
So when you implemented the nighttime, can you combine the equalities?
What do you mean by combine equalities?
Well, you've got the tilde now that says that.
So the idea behind these convertibility assumptions is that the user should never be able to, should never explicitly refer to them because it should be an automatic process. But for this to be well behaved, so for example, Haskell has actually something a little bit like this. It has like type equality constraints. But Haskell's constraint solving is not at all complete. So it fails like transitivity, it fails congruence. So in practice, you still have to do some manual work because you have to create these intermediary definitions which might type check, even if the full thing doesn't, right? And do it step by step. So the idea here is because we have more complete type checking for this type of equality, the user should never need to refer to it, but combining different equations should happen like automatically because we say this has to be an equivalence relation, and then we make sure it actually is an equivalence relation.
Yeah, so go back to my question.
Yeah, sorry, maybe I misunderstood.
You never promoted to equality.
So if you want to turn this back into a propositional equality, that's actually really easy because that's just, so how you introduce propositional equalities is with reflexivity. So if both sides are definition equal, you get a propositional equality. That's standard in type theory, and that works here as well, right? Because if we have both sides definition equal modulo these equations, well then we still just type refl. I mean, it's like in our type checker, right? We are still returning a propositional equality. How do we construct it? We just write refl.
Anybody in the audience brave enough to ask a question? Because it's type theory.
Will anybody ever accept this? I mean,
Yeah, it's a good question.
in the time of LLMs, and everybody is using just some undefined system which gives something back, and that is good enough. While my experience with type checking, I mean, with proof assistance or whatever, it's more work than it's really worth for an engineer.
Get out of this room.
Thank you.
I'm asking if an engineer
Yeah.
use this.
So I mean, I think this is quite close to something that you could implement in Agda. Oh, so I think the people that are using Agda at least would enjoy this.
Yeah, I'm sure. There are people who can have endless discussions about chess problems and
No,
code
the field
problems.
proofs are used.
Yeah.
Field proofs are used. People do a lot of work. The best part is that developing their own.
Yeah, but okay, good. No,
Yeah.
I'm just
Yeah, I don't know. I think
You just
don't misunderstand me. I'm not rubbishing this, but under no circumstances. But for example, you say programmer. Development at the moment is that I think I read recently in The Economist, 2/3 of all programmer jobs are gone or are leave.
I know a lot of
They
people
throw them
paying
out.
nice amount of money to just write code.
Oh, okay, now you are going a little bit outside the model.
Yeah.
I don't know. To very quickly say something, I feel like okay, even if vibe coding becomes very popular in specific domains, right? Like even if like I think we do still care about secure software you can actually trust, right? And for that you need to write precise specifications. You can't expect a probabilistic model to like come up with a precise specification.
You rubbish what I like. Be careful.
Oh, sorry.
Very well done. I think
I'm not talking. No, I mean, one can reason about probabilities in a very.
Sorry, I'm not talking about your research, I'm talking about LLMs, yes, sorry.
Okay.
Yes. I need to make that clear what I'm talking about here. Yeah, sorry, yes. I'm not talking about program analysis, no.
Black box pseudo statisticians or something like this.
Sure, yeah. Yeah, maybe that was a bad word choice.
You
Sorry.
stop here.
Okay,
Thank you very
cool.
much.
Thank you.